Hello, welcome to my channel RD Physics. I am Dr. Rashmi Deshpande and this is a course on atomic and molecular physics. This is lecture 8 from the series and today we are going to discuss about the electron probability density in the hydrogen atom. So if we consider Bohr atom model for hydrogen, then the electron is considered to be revolving in a circular path as shown in the diagram. So an electron can be found at a distance of r equal to n square a0 from the nucleus. Here the nucleus is considered to be at the origin of the coordinate axis, and this is the electron which is revolving in a circular orbit around the nucleus. So the orbital plane of the electron is fixed in this case. This is xy plane. So the electron is moving in the equatorial plane. So theta is equal to 90 degrees and phi is changing with time as shown in the diagram. So theta, that is angle made with the z-axis, with the angle made by the position vector with the z-axis is 90 degrees, and as the electron moves in this orbit, the theta angle keeps on changing. But remember, according to this Bohr atom model, because the electron is moving in this orbit, the plane of the orbit is fixed. In the above equation, n is principal quantum number of the orbit, which can take values like 1, 2, 3, 4, etc. And a0 is radius of the innermost orbit, that is when the electron is in the ground state. So this is called as Bohr radius and it is approximately 0.53 angstrom unit. But according to quantum theory of hydrogen atom, we cannot give definite values to r, theta and phi. We can give relative probability of finding the electron in volume elements at different locations. We know that quantum mechanics is probabilistic in nature, so we cannot define the electron orbit as it is done in Bohr atom model, but rather we can talk in terms of probability of finding the electron around the nucleus. So this probability, we know that it will be given by mod psi square, rather probability density of finding the electron around the nucleus will be given by mod psi square, where the wave function of the electron is psi, that is a function of r, theta and phi coordinates, and it is a product of three functions, that is capital R, which is a function of variable r, capital theta, which is a function of zenith angle theta, and capital phi, that is a function of uh, angular displacement phi. Okay, so psi is a product of r, theta and phi, and so the probability density will be equal to mod of psi square, that is mod r square into mod theta square into mod phi square. Now one by one we are going to discuss about all these three probabilities, that is probability which depends upon the radial variation, probability that depends upon the zenith angle theta, and the probability that depends upon the azimuthal angle phi. So first of all, because we know what is the phi wave function, so therefore let us discuss first what is the azimuthal probability density. We are going to show that it is a constant for the electron in hydrogen atom. So we know that capital phi function, that is phi function, is written as a into e raised to I ml phi, where ml is the magnetic quantum number. So mod phi square is nothing but a square, which is equal to a constant because a is normalization constant. So electron's probability density is symmetric about z-axis. For all the quantum states, it does not depend upon phi. Okay, because a square is a constant, that means for all values of phi, the probability is not going to change. So can we find this normalization constant A? The answer is yes, because we can use the normalization condition, that is integration of mod phi square d phi, where phi varies from 0 to 2 pi is equal to 1. This is the normalization condition. So if we substitute for this phi function, then we get that mod a square will be equal to 1 upon 2 pi, so that a will be equal to 1 upon root 2 pi, and the normalized form of wave function phi will be 1 upon under root 2 pi e raised to iml phi. So one thing is clear, that the azimuthal probability density is mod phi square, that will be equal to 1 upon 2 pi. Okay. Now what is the zenith probability density? That is mod theta square. We are going to show that it is we are not going to prove it, but it is known from the wave function theta, because we are not discussing the wave function theta, but from the wave function theta, the zenith probability density varies with the angle theta for all states except for S state. Okay, for S state, mod theta square is constant and it is equal to 0.5 or half. So we know already that mod phi square is constant, and now for all the S states, mod theta square is also constant. So that means mod psi square will depend only upon mod r square for all the S states. Thus, the probability density of finding the electron in S state depends only upon R. That means it is spherically symmetric. It does not depend upon the angle. So therefore, we can say that it is spherically symmetric. Now let us consider the radial probability density. The probability of finding the electron at a distance between r and r plus dr from the nucleus is proportional to mod r square dv. Okay, because the probability of finding the electron at a distance between r and r plus dr means between the within the shell, which has inner radius r and outer radius r plus dr. So we will have to consider the volume of that spherical shell, that is dv. Okay, and so the probability will be equal to 4 pi r square into mod of r square into dr. So we can see that this radial probability, it depends upon r and the function capital R. So if we plot PR as a function of R for different energy levels, that is 1s, 2s, 2p, 3s, 3p, 3d, then we will obtain some graphs that we are going to discuss in the following slides. So let us consider if n is equal to 1 and L is equal to 0, that is 1s state. So if we try to find out the, if we plot the graph of radial probability against the distance r from the nucleus, then we get a graph like this for the 1s state, which shows a peak at a0. So for n is equal to 1 and L is equal to 0, that is 1s state, there is a single maximum corresponding to most probable position of the electron at r equal to a0, which is nothing but Bohr radius of first orbit. Okay. So the maximum is obtained at distance a0 from the nucleus. If we consider 2s state which has n equal to 2 and l equal to 0 again, then we observe that there are two maxima. We can see here there are two maxima, one is smaller and the other one is a bigger peak. So first one is low and small, second one is high and broad. So if we consider this, means if we consider this probability, then we can see that the small peak which we are observing here, we can say that in a two-dimensional picture, the electron probability is somewhat like this because of this small probability, and the bigger peak is shown in this fashion around the nucleus. So this is like a two-dimensional picture which we are considering, corresponding to this graph of 2s state. So we can visualize the probability of finding the electron in 2s state around the nucleus will be somewhat like this. If we are considering n equal to 2 and l equal to 1, that is 2p state, then see in 2p state there is a single peak 4a0 at r is equal to 4a0. There is a single broad hump with maximum at 4a0. Again, a0 is Bohr radius. So if we plot this, means if we pictorially represent this probability of finding the electron in 2p state, then because there are three values of ml, that is ml equal to 0 and ml equal to plus minus 1. So a two-dimensional picture of electron probability density will be something like this. For ml equal to 0, for ml equal to plus minus 1. We can obtain the three-dimensional picture if we revolve these pictures around the vertical axis, because the probability is not changing, probability density is not changing with angle phi. For all the states, there is no change in the probability with respect to phi. So we can rotate it around z-axis and we will get a three-dimensional picture of it. If we consider 3s state which has n equal to 3 and again l equal to 0, we can see here that there are two small peaks and one broad peak for 3s state. Again, if you look at the two-dimensional picture of probability, then these two smaller peaks, they are depicted here, the inner one and the outer small, and the bigger one that is corresponding to this broad hump is the outermost circular pattern. Then for n equal to 3 and l equal to 1, that is for 3p state, there is a small peak and a broader peak. Again, here we can see for ml equal to 0, this is the pattern in two-dimensional picture, and for ml equal to plus minus 1, this is the pattern. For 3d state, that is for n equal to 3 and l equal to 2 state, there is again a single peak and means there is a we can say a broad hump with peak at 9a0. So for 3d state, the peak is at 9a0 and the corresponding two-dimensional patterns are shown over here. For ml equal to 0, for ml equal to plus minus 1 and for ml equal to plus minus 2. So in each case, that is for n equal to 1, n equal to 2 and n equal to 3, we have seen that for highest permissible value of L, that is for L equal to n minus 1, we observe that the probability of finding the electron in hydrogen atom is maximum at R equal to n square A0. That because for 1s state it was maximum at A0, for n is equal to 2 it was maximum, for 2p state it was the maximum was observed at 4a, r equal to 4a0, and for n equal to 3 the for 3d state the maximum was observed at r equal to 9a0. So that is nothing but the radius of corresponding Bohr orbit. Means according to Bohr atom model, the electron will be found at a distance r equal to n square a0, where n is principal quantum number. So the radius of Bohr orbit as given by Bohr atom model is same as the most probable location of the electron as given by quantum mechanics. So Bohr model gives the most probable location of the electron in several possible states, because for example when the electron is in n is equal to 2 level, there are possibilities of finding it in 2s and in 2p level. But if it is in the 2p level, then the maximum is observed at 4a0. So that is the most probable location by using quantum mechanics, and it is in agreement with the prediction of the Bohr model. So these two theories are giving the similar result. So if the students want to watch a detailed discussion about this, then you can refer to this particular lecture on YouTube. The link is given over here, and a detailed discussion can be observed on this link. Thank you very much.